Okay, let's get started. Let me share my screen. Everybody, can you see my screen?
Yes, sir.
The title is Synchronization or Parallel Operation of Synchronous Generators. Uh, as you can remember that in last class, we were discussing this. We just started this one. Today I will explain. Last class we explained what is the reason to connect many generators in parallel. So we understood those reasons and what are the conditions that you connect two generators in parallel. So therefore, everybody see, I have written like 4 points. The first point is RMS voltages of the incoming generator must be the same as those of the infinite bus or running generator. So this means that you have one generator already in service. For example, one generator is already running and you want to connect a new generator in parallel to the existing one. So therefore, when it says infinite bus or the running generator, meaning that that is already in place, it is running in the system. And you want to bring a new generator, which is called the incoming generator. So therefore, what it says, the RMS voltages of the incoming generator must be the same as those of the infinite bus or running generator. So therefore, through diagram, I am explaining you and how you will make sure that the voltages are the same. The second point, the phase sequence of the voltages of the incoming generator must be the same as that of the running generator. Again, other condition, your running generator means the current or existing generator has a particular phase sequence. For example, ABC or ACB. Now the new one, the incoming generator, that also have the exactly the same phase sequence. So now that's the question. How would you understand that the incoming generator has the same phase sequence as the existing one? The third point, you see, the phase voltages of the incoming generator must be in phase with those of the running generator. This means that, for example, for the running generator, current generator, the FH voltage VA VM cosine of omega t plus 10 degree, just an example. So exactly the incoming generator for phase A, that also should have the 10-degree phase angle. That is the meaning. So that is the phase voltages. So number 2 is phase sequence. Number 3 is phase voltages. Must be the in phase with the running generator. Number 4 is the frequency of the incoming generator must be almost equal to that of the running generator. In fact, here again, the frequency must be the same, but initially it said almost equal. There is a reason. So later I am explaining that why it said almost equal, not say like must be equal, similar to point 1, 2, 3. So anyway, so everybody keep in mind, these are the 4 conditions that must be fulfilled, that must be made to connect two generators in parallel. So the question is, if any of the condition does not meet, then what will happen? So those things we will discuss today. So therefore, this is pretty interesting. Let me take you to the board, and then it will clear to you. Hold on. Okay, so everybody see the, for example, you have one generator, which I am calling this is the running generator. This is in the system, for example. So therefore, this is A phase, this is B phase, and this is C phase. So let's label this one. This is the running generator, or it is called infinite bus. Okay, and then here assume that there is a new generator. This is the new generator that we want to connect in parallel with this generator. So for example, sorry, it has the switch. So yeah, our final goal is that we will be closing this switch like that. You see, that is our ultimate goal. And then let's say this is also F H, B H, C H. Let's designate A prime, B prime, C prime. Now let's label this on. This is his incoming generator. Sorry, incoming. This means this will be the new generator that we have bring into synchronism or in parallel with the running or the infinite bus system. That is the meaning. So therefore, let omit this thing. Yeah. At last, we will connect, making sure that all four conditions that I showed you in the previous slide have been fulfilled. Now, let me draw its shaft system as well. Okay. Of course, it has its own shaft. Yeah. Okay. So now everybody see the the first condition is that the RMS voltage that we learned, the RMS voltage of the incoming generator must be equal to those of the running generator. Now, what is the meaning of that? What you will do, you will be connecting a voltmeter here. For example, you have a voltmeter here. So you measure this voltage, line to line voltage. Now, for example, you got that line to line voltage is 208 volt. Now you start the new generator, incoming generator, its shaft is moving, and of course we are assuming that it has a magnetic pole, north pole, south pole. You excited, and it started producing voltage. And then now you connect the voltmeter here. You connect the voltmeter here. I mean, so between this point and then this point, you measure the line to line voltage. And then because generator just restarted, gradually voltage will build up, build up, build up. You adjust the shaft, you adjust the magnetic field. By adjusting those two parameters, speed and the magnetic field, you match with the 208 volt. Therefore, for example, you also got the 208 volt. Then you stop there. You don't increase the speed. You don't change any of the field. So now this ensures that, okay, the running generator or in existing generator has 200 volt line to line voltage, RMS voltage, same thing, you got that. So this means number on condition is fulfilled. So you can easily guess that because you have to connect this switch with this one that I was telling you, before connecting, you have to make sure that the voltage here and voltage here is the same. So if the voltage is not the same, you see, then what will happen? For example, you connected, just an example, and then, for example, it is not 208 volt. Sorry. For example, its voltage is just 200 volt. You got, and then you stopped. You said, okay, now it is pretty close. There is only 8 volt difference, so it is safe. Let's connect it. You connected. So can you guess what will happen? Will there be any current flow if it is 208 volt and this side 200 volt? What will happen? So definitely current will flow, right? So if you see this is one point and this is other point, and you connected, in this side you have 208 volt and in this side 200 volt, right? So therefore, what is the condition of current flowing? So from higher voltage to lower voltage, so current will start flowing in this direction, right? So and then if the current flows, so then definitely these cables, these connecting cables have, even the small resistance, they have resistance. So once current will start flowing, there will be I square R loss. because even though it's small, there is some R between these 2 points. So therefore, there will be power loss. And what is the power loss? It will expose in terms of heat. Heat will be generated, so which is not desired. Therefore, when you will be connecting two generators in parallel, their voltage must be the same so that there is no circulating current from here to here. Once you will connect, their voltage will be the same, and that will contribute to the load. Current will flow towards the load side only. Something is coming from this generator, something will coming from this generator, and both will contribute towards the load, customers only. It is not expectation that current will flow this way or this generator will send power this way. For example, you made this on 220 volt, just an example. So if it is 220 volt and this side is 208 volt, then current will start flowing from this side to this side. Then again the same problem. There will be I squared, there will be heat generated and undesired losses. So parallel connecting means you want to support the customers. You want to contribute to the loads only. It is not your goal that this generator and this generator will exchange power. Everybody, could you follow me what I am saying?
Yes, so far so good.
Oh, great, great. Yeah. So therefore, let's say like I will not connect this one and I am deleting these things. So this means, okay, at this point, everybody understand. We, that first condition is fulfilled. This means just an example. I produce 208 volt by adjusting the field flux and the speed. Now come back to the phase sequence. You have to meet all of those four conditions. So how would you understand that this A phase, B phase, C phase, and here A phase, B phase, C phase, they have the same sequence? How would you understand that this is not ACB or this is not ACB? How could you understand? How can you verify that? You must verify that. So therefore, to understand that, what you will be doing, first, because this is your existing system, the running system, I think that I deleted. Let me once again, this is running or the existing one. So here, first you will be connecting a small size of three-phase induction motor. Three-phase induction motor. This is IM, three-phase induction motor. And then first you connect. This is A phase, this is B phase, and then this is C phase. And then, for example, this induction motor had clockwise rotation. That is indicated, that is defined. So therefore, you notice that in the running system or in your existing system, induction motor is properly following the given direction, prescribed direction. And then now you take it out. You take it out, this induction motor, and then you connect it here. You connect it here. Okay, this is that same induction motor. It has three terminal. Again, you connect A phase and then B phase and C phase. And then you notice that, okay, again, it is also rotating in the same direction, clockwise direction. This means that phase sequence is fine for the existing system, running system, or the new or incoming generator. So therefore, just by starting an induction motor, you could understand whether the phase sequence correct or not. Now if it would be rotating in the reverse direction, meaning that this phase sequence and this phase sequence is not the same. So in that case, before we discussed what you would do, you interchange. For example, this is A prime, B prime. Assume that this is your B prime and then this is your A prime. So therefore, when you will be connecting, you will be connecting this line there and this line there. And finally, you need to interchange or swipe any of the two leads. Then the direction will be fixed. That is the meaning. So therefore, in case of the motor, you just swipe. You connect A phase here and then you connect the B phase there. And then you will notice that next time induction motor is running properly. and the direction is the same as to the original for the running generator or existing system. So in that way, you can make sure that your phase sequence is okay. Now, as I told you, you will be doing this experiment. This is, I think, lab number 6, connecting 2 generators in parallel or synchronous. Exactly, you will be doing this lab in the laboratory. So what you will be doing, instead of starting an induction motor, we have the lamp system. I am deleting these things. It is called the synchronizing lamp. Let me write down the terminology. It is called synchronizing lamp. This means with the help of the lamp, you can test the phase sequence. So what is the method? What you will be doing? For example, you have one lamp here. This is one lamp. Connect the lamp here. And then you have the other lamp, second lamp. You connect here and here. And then you have the third lamp. You connect here with FH and then with here FH. So therefore, as you can see, 3 lamps are connected with 3 phases, corresponding 3 phases. So what will happen? And then you are making sure that they have the same phase sequence. So if they have the same phase sequence, both the running generator and incoming generator, all 3 lamps will have the same level of brightness. All 3 have the same level of brightness. But if you see that the brightness level is different, meaning that there is phase sequences. So therefore, if the voltage here and voltage here is the same, so therefore they will be glowing at the same time, or they might be go fully dark at the same time. There will not be difference in their brightness. So everybody, do you understand? So you will be connecting the 3 lamps in that way, and you will be noticing their brightness, whether all 3 have the same level of brightness or not. Do you see that, okay, one lamp looks like very dim and one looks like very bright? That is the phase sequencing. So you will be noticing their brightness. Is there glowing equally or not? That is meaning that the phase sequence is correct. So, and then if you understand that the phase sequence is correct, and then also the RMS voltages are equal, then typically the phase angle for any of the phases here or any of the phases, they are in the same phase. I mean, there is no phase difference. So you are fully fine. Now the last point is that how about the frequency? How will you test the frequency? So therefore, to understand the frequency, so again, so you have to make another test here. You start this generator, and then there is one device. It is called the synchroscope. It looks like that. Okay. So this is a pointer. This side is like fast, and this side is slow, and this is called synchroscope. Let me write down that. Yes. It is called the synchroscope. Synchroscope means this is a device to understand the frequency. So therefore, this is a device. What will happen? As I said that in the slide when I was showing you several minutes back, the incoming generator frequency should be little bit higher than the running generator. That is initially. So therefore, for example, for the running generator, your frequency is 60 hertz. That you know, because this is your existing system already in practice. Now you started this generator and gradually voltage build up. You reached up to that level of voltage and you verified the phase sequence. Everything is fine. The last thing you are testing, what is the frequency? Therefore, you have the prime mover. You can control the speed. What you do, you increase the speed a little bit. So, I mean, look that equation. So you all know here the speed is, sorry, speed is n equal to 120 f over p. So therefore, what I am saying, then initially you keep the frequency a little bit higher than 60 hertz, for example, 61 hertz or 62 hertz. So how you will get that? Because pole number is fixed, you can increase the speed, this one. So in the lab, you can control the prime mover speed. You do that so that your frequency is little bit higher. So therefore, you see this synchroscope, it will indicate in that direction. In the first, this side is slow. This means that this is the perfect position. This is the 60 hertz position. In the synchroscope device, there is a needle. This is the needle or the pointer. If that indicates at this position, meaning that it has the 60 hertz. If it is more than 60 hertz, then the indicator will be in that direction, here or here. So that's why I have written it is the fast, this side is slow. If it is lower than 60 hertz, pointer will indicate here or here. So therefore it depends on the how you are adjusting the speed. So therefore, as I said you, initially it will be needle will be in this direction, in the fast direction. That is the indication that your speed is little bit higher than this generator and the frequency is also higher. Why you need that on at the beginning? To ensure that this will work as a generator, not as a motor. Because when if the frequency is low, your speed is low, and if you connect this three phase, assuming that okay, all conditions are met, it might happen that this generator started taking power from this generator instead of giving power to the common bus, to the common point. So therefore, taking power means this may work as a motor instead of a generator. But we don't want that. That's why at the beginning, you keep this speed little bit higher so that the frequency is little bit higher. Then it will not be a motor. Definitely, it will be a generator. Speed higher means your mechanical side is dominating. You have the enough speed so that there is no chance that it will work as a motor. Definitely, it will be generator. So therefore, and once you do that, then gradually you adjust the speed when the needle will indicate exactly at this position, meaning that now it is the 60 hertz. So therefore, you will be connecting this one, and then immediately you will adjust this shaft little bit so that the needle indicates here. It is neither fast nor slow, exactly what is needed. That is the indication that your frequency has matched with the running or the existing system. So in that way, you can ensure that all four conditions have been met. So again, the first one is RMS voltages of the running generator must be equal to the RMS voltage of the incoming generator or the new generator. The phase sequence of the running generator must be the same as that of the incoming generator. The phase voltages of the running generator must be in phase with that of the incoming generator. And then the frequency of the running generator should be almost equal to the incoming generator. That's why we are using the term almost equal, because at the beginning I had to keep the frequency a little bit higher to make sure that the new generator, incoming generator, will properly work as a generator. And once you do that, and then you adjust to match with the exact frequency. So once these four conditions are fulfilled, then it is safe. Now you connect. Now you connect. There is proper synchronization switch. These are called the synchronizing switch. This means this generator is now in parallel with this generator. Now it is safe to deliver power to customer. Now you send to the load. This is the load side. Because all four conditions have been made. Now there is no chance that there will be any circulating current from here to here or from here to here. All will go towards the load side only. So therefore, I mean, this is in real practice. This lab numbers, this is exactly in real practice. This is available. So before connecting any new generators in parallel, power operator verifies those four conditions. When those four conditions are met, satisfied, only then the new generator is connected in parallel with the running or existing generator. So everybody, could you follow me? Therefore,
Yes, yes, I could.
yeah, therefore, if you see the lab number 6, I mean, already I have posted everything on eCourseware. If you, I mean, one thing is that LabTO made the video, that is one thing, but before the video, there is also experimental description, experimental sheet. So therefore, once again, you can read. So exactly this thing that I explained here is available in that document, experimental description document. You will be getting that up. So now I am taking you that. You see? Therefore, you will be remembering these 4 points. You have to remember these things exactly. Whatever way you explain, but you must, each of you must remember these 4 points. This is very, very important to a meeting. Now the question is, I mean, I will be asking you the question, if any of the conditions does not meet, then what? So then I was explaining you, if any of the conditions does not meet, and then you switched in, you connected, or you made the parallel, what will happen? There will be circulating current flow from one generator to other generator. And that circulating will current will cause some loss and heating in the system. And that is not desired. And that is the reason. Now think that, for example, United States has 60 hertz system, right? All over United States. I mean, all over North America, 60 hertz. And now European country and Asian country, they have 50 hertz system. So for example, then you are traveling and you went to Europe. Now you have a device here, for example, your hair dryer. Your hair dryer is based on 60 hertz. And then you are staying in hotel, going Europe or going Asia, and then their system is 50 hertz. So then how would you connect? So if you connect your device to their 50 hertz system, what will happen? Meaning that last question is not meeting, last point is not meeting. Frequency of the incoming generator, I mean, that is not generator, that is the plug point, but it's still the same meaning. So your system is not matching with their system because different frequency. So what will happen? Maybe immediately your hair dryer will not burn, but after several minutes it might be burnt because there is frequency difference. There will be circulating current flow between your device and their system, their plug point. So that's why when you'll be going abroad, I mean Europe or Asian country, so whatever. So if the frequency is different, you should have that international things. There should be frequency converter. The same thing, not only that hair dryer, for example, some device, you have 60 hertz and their system is different. Again, you will face the same problem. And also, here the voltage is 120 volt, or we say 115 volt, but in Europe and Asian country, their voltage is 220 or 230. The same thing, voltage is also not matching. Therefore, for example, you want to charge your cell phone. So therefore, you must have converter. You must have internationally adapted converter. Otherwise, you cannot plug into their system because your voltage is 120 and their voltage is 220. So again, immediately it will be burnt off. So therefore, these are those regions that why you cannot connect on generators having on voltage with a different generator that have different voltage. That's why you must make sure that all four conditions are met. Only then two devices or two generators can be connected in parallel. And then, as I said, if any of the condition does not meet, then there will be circulating current flow. Your device may be burnt up, there might be heated, immediately might not be burnt up, but over the time it will be burnt up because of gradually circulating current flow and getting heated up and heated up. Okay, now here you see, I wrote down on term, it is called infinite bus. That was, you see, in the first point I wrote, must be the same as those of the infinite bus or running generator. So running mean that is the existing generator, existing system that I am telling infinite bus. So what is the, as you can see by the name infinite means unlimited. So that's why the bus at which the voltage and frequency are almost constant always. Meaning that in the power network, there will be a common point or a particular conductor which is called the bus where the voltage and frequency will remain always constant, of course within a certain limit. Let's say if the power flow is 1000 megawatt up to, then the voltage and frequency will not change there. Typically if you connect more and more load, the voltage should go down. The frequency might also be changed. But it is called infinite bus. Within a certain limit, whatever load you connect at that point, the voltage and frequency does not change, always remain constant. That's why it is called infinite bus, like unlimited bus. Therefore, why I am telling, I mean, not only here, so in other place, in this book or any other book, or you are listening to someone's lecture, they might use this terminology, infinite bus. So that time you will understand that, okay, it's a conductor, it's a specific bus where the voltage and frequency are constant. That is called the infinite bus. So, everybody, could you follow me so far?
I understand so far.
Yeah, sure can.
Great. So everybody, this slide is your lab number 6. And then that diagram, exactly you will be doing this thing. And this thing is explained in the experimental sheet. So please you see, and it will be lab number 6. Still you have about 2 more weeks. So you will be fine. Now moving forward, here you see that power and torque characteristics of synchronous machine. Now, you see in the last class, we are drawing the phasor diagram, under excitation, over excitation, normal excitation, I mean, leading power factor, lagging power factor, unity power factor. So how can we express the power? And you see there was one angle delta, which was called the power angle between the terminal voltage and internal generated voltage. So therefore, to express the power in three-phase synchronous machine, you will be using this equation, 3 EA V phase over Xs sine delta. So therefore, Xs, this is that synchronous reactance. You remember, we are solving one problem where there was armature reactance and the leakage reactance. The sum of those two reactants is called Xs, synchronous reactance. And EA is that internal voltage. I have defined here, internal generated voltage. And that V phase, this is the terminal voltage. And 3 is multiplied because this is three-phase system. Therefore, everybody assume without 3, if I don't multiply by 3, this will be for single phase system. So meaning that this Xs is per phase for one phase. Similarly, EA, V phase, those are for per phase, for only one phase. I mean, why I am emphasizing this, soon we will be looking at numerical problem. If it is Y connected system, then, to get EA and V phase, you have to divide those by √3 line quantity. If it is delta connected system, then line voltage, phase voltage are same, it is fine. But if it is Y connected system, you have to be careful. Therefore, everybody in this equation, keep in mind that EA and V phase, those are the phase quantity, per phase quantity. That's why for three-phase system, 3 is multiplied. And delta is the torque angle or the power angle. Now here I have written the next one, you see, because it is sine delta, you all know the maximum value of sine delta can be 1. So that's why that is the Pmax, just this portion. Similarly here, this is the torque. So in case of torque, you see, everything is the same. You are dividing by the speed. This is speed in radian per second. So synchronous speed in radian per second. And then this equation shows Q, this is means the reactive power. So this is the active power or the real power for synchronous machine. And this is the expression for reactive power. Now, what I would recommend you, so I believe everybody right now you have your pen and paper. Can you please write down this equation, this phi, and then this Q equation in your note? And then in next slide, there is a numerical problem. Right now, upfront you solve in your calculator using those equations, and then let me know the result here. So everybody, please write down this equation in your note. This. You please write down this equation and then this Q equation in your note. Once you are done, then please let me know. And then of course, you note down the meaning of the symbols. EA, as I told you, internal generated voltage. V phase, terminal voltage. Delta is the power angle or torque angle. And XS is the synchronous reactance. And then those symbols are used in this equation, Q equation, reactive power. So you are fine. Just once note down the meaning of those symbols. So have you all written down in your note?
I got it.
Okay. So everybody, have you written? Okay. Have you written down Q as well?
Yeah, I've got the whole slide.
Okay. Okay. Great.
Yep. Just
Okay.
finished writing.
Okay. Thanks. Now everybody, please read this problem first. A three-phase 13.2 kV, 60 Hz, 50 MV, two-pole, Y-connected cylindrical rotor synchronous generator has a synchronous reactance of 3.0 ohm per phase. If the internal generated voltage is 15.0 kV and power angle is 30 degrees, then calculate the torque of the generator. So this means that for this problem, at first you will be calculating the power. You all will be calculating power by using this equation. And once you get the power value, then the question is calculate the torque. You will be dividing by the speed in radian per second. That's all. So everybody see, you have to use this equation. So please use this equation and then let me know what power value you are getting. And then to calculate the torque, you divide the obtained power by the speed. So how you will get the speed? From the very first line, you see, 60 hertz and 2-fold. So which equation you will be using? N equal to 120 F over P. N equal to 120 F over P. Then you will be getting that speed in RPM, then convert into radian per second. So first everybody use this information and calculate that power and let me know what is the power value you got. Everybody please try. So when to use that equation, everybody keep in mind which one is the terminal voltage. Which one is the terminal voltage in this problem?
The 13.2 kV.
Exactly, right. Yeah. But keep in mind, this is very first one, this is three phase. So this is three phase, meaning that, everybody listen to me, meaning that 13.2 kV, that is the line to line. As I told you before, in real practice, in real system, always this voltage is expressed in terms of line to line quantity. If it is phase voltage, it will be clearly mentioned. Because it is not mentioned, meaning that by default, this is line to line voltage. And then keep in mind that the last, it is Y connected. So three phase Y connected, this is line to line voltage. But then what I said that in that equation, these are the phase quantity. That EA, terminal voltage, V phase, both are the phase quantity, not the line to line. Everybody please listen. These are the phase quantity. So this means that you have to convert this on into phase voltage. Similarly, everybody look at the fourth line. If the internal generated voltage is 15 kV. Now again, it does not say that this is phase voltage. Because it does not say phase voltage, by default, this is also line to line voltage. Line to line voltage. This means you have to convert this voltage into phase voltage. Therefore, both voltage, both 13.2 and 15, you have to convert into the phase voltage to use into that equation. And then you see power angle is 30, so definitely this is delta. And then now please let me know, first let me know, what is the power that you got, real power. And then later you let me know what is the torque. The torque will be power over omega. Omega is in radian per second. That you will be getting from pole number 2 and frequency 60 Hertz. So is everybody trying with your calculator? So therefore, you see, synchronous reactance has no problem. It is clearly expressed per phase. So therefore, you don't need to do anything with the synchronous reactance. Is it as it is? It is per phase. So only you have to convert those to voltage per phase, because that is Y connected system. And delta is given. So, and then of course, 3 will be multiplied here. So what is the power value that you are getting? What is the amount? So once you get, then please let me know.
I got like 33 megawatts.
Exactly right. Exactly. That is the correct answer, 33 megawatt, the power. And then now you keep going, you calculate the torque. The question is calculate the torque. So torque means that power that you got, 33 megawatt over omega. I mean speed, but that speed is in radian per second. So therefore, as I said, from the very first line information, 2 pole and 60 Hertz, using those two information, calculate the synchronous speed. What is the synchronous speed? 120 multiplied by F over V. But that will be in RPM. You have to convert into radian per second to use in the torque equation. And then let me know the final torque value. Is everybody got the same value? 33 megawatt P value?
For torque, I got 87,535.22.
Is it in Newton meter?
Yeah, it'd be a Newton meter.
Yeah. Like I expressed in kilonewton meter, 87.53 kilonewton meter. I think the same
Yeah.
thing, right? 87.53 kilonewton meter. I expressed in that way. Okay, so then like you are fine. So what is your speed, synchronous speed in radian per second? Is it 377?
Yeah, it's 377.
Okay, so right. So everybody, so are you getting the same values? I mean, I have done it in the next slide, but without showing you, I like you that you please do it in your calculator so that it will be practice.
I'm getting the same numbers. Or
Same number?
do.
Okay. So P value is 33 and torque value is 87.53 kilonewton meter approximately. But if you don't get the correct value of phi, then you will get different value of torque. Yeah. So first you have to make sure that you are getting correct value of phi, 33 megawatt. So I'll be asking you a similar problem in the upcoming midterm exam too. Very similar thing. That time you have to use this equation. I think in the homework I did not give the similar problem. I have given different problem in the homework. But in the midterm exam, again, you might expect this type of problem. Okay, so therefore, everybody, those who are still doing, so see my handwritten calculation, everybody look this on, and then you match that where you are making wrong. Everybody please look this on. Like this is 3 and then a 15 over root 3 kV. Terminal voltage V phase 13.2 over root 3 kV. I am dividing by root 3 because see the problem, that is that the end of the first line, this is Y connected system. And I said, these are the both 15 and 13.2 are line voltage, line to line. So that's why I'm dividing by root 3. XS is already expressed in power phase system. And then this is sine 30 degree, I got 33. And then look torque tau, V over omega Newton meter. That 33 and omega, you see right side, NS synchronous speed 128 over P, 3600 RPM. Then I converted into radian per second by multiplying by 2 pi and dividing by 60. And then I plug in this 377 there. So finally I got 87.53 kilonewton meter. So everybody, are you matching with your calculation this one? And then you see that where you made mistake or you got the same thing. Is everybody fine? Should I move forward or still you're calculating?
I think we're good.
Sorry?
I think we're good.
Okay. And then actually I just liked you that you do. That's why I did not show this slide at first. I could show. I like that. Okay, you also make practice sometimes. Okay, so therefore moving forward, like we are done with most of the talks about the synchronous generator. From now on, I will start synchronous motor. You see that before we started the induction motor and then also induction generator. So today we will be looking synchronous motor. So therefore, in real practice, in industry, although in most cases induction motors are extensively used, but there are some application of synchronous motor. So therefore keep in mind, in case of synchronous motor, as the name goes synchronous, the meaning of the synchronous is that its speed is almost constant. Speed is constant. This means you have to choose the application where the constant speed operation is needed. So on the other hand, induction motor, its speed is not always constant, especially if it is wound rotor type of induction motor, then its speed is varying. So consequently, induction motors are used where you need variable speed operation. And then synchronous motor means its speed is constant. So those are the application, like paper industry, mill industry, where the constant operation is needed, not the variable operation. Okay, so now then with regard to synchronous motor, there are a couple of things. You see, I have written a role of damper winding in synchronous machine. There is one term, and then again, those things will come. What is the phasor diagram of synchronous motor? What is the effect of excitation on power factor? If it is leading, lagging, or unity, then is it overexcitation, underexcitation, normal excitation? And then two important things, it is called V curve and inverted V curve for synchronous motor. Pretty interesting. One curve look like the symbol or the letter V. Accordingly, it is called V curve. And then other curve look like the inversion of V, like inverted V. That's why it is called inverted V curve. I will show you. And then one pretty interesting thing you see, synchronous condenser. Synchronous condenser, the meaning of condenser is capacitor. Capacitor, meaning that synchronous motor can work as a perfect capacitor. You know that in case of the capacitor, current leads voltage by 90 degree, and that's how it is able to provide the reactive power. It can improve the power factor. Exactly the synchronous motor, under a certain case, under a special case, it is called synchronous condenser, meaning that it behaves perfectly as a capacitor. The same thing. This means synchronous condenser can be used to improve the power factor. Exactly the same function of capacitor. This is pretty interesting. I mean, your motor will run, but then it will behave as a capacitor, meaning that if you see its voltage and current relationship, current will lead voltage by 90 degree, and then we will call it the synchronous condenser. Very interesting. So we will be looking these things. And then the last thing will be the power angle curve. So now, first of all, to understand these things, synchronous condenser, V curves, to understand all of these bullet points, first you have to understand the synchronous motor principle. Then you will be able to understand all of these. So therefore, let's have a look. Everybody see, I have written one thing. Synchronous motor is not self-starting. And I have written then the induction state, that dash synchronous run motor. So meaning that because synchronous motor is not self-starting, initially it can't start. Initially it can't start. But because it is motor, somehow we have to rotate it. So that's why initially we need induction principle to start, and later it will run as a synchronous motor. That's why sometimes, instead of just synchronous motor, if you see this book or any other literature, its other big name is induction start synchronous run motor. Ultimately synchronous run motor, but synchronous motor, but first it will start with the principle of induction, and later it will be synchronized to provide you a constant speed. Now, what does that mean? Why I said that it is not self-starting? So let's have a look. Okay, let me clean up all of those things. Oh, so I think I just something came in my mind. So I think I need to mention you. I think you have done lab number 1, lab number 2. Lab number 1 was about 3-phase system. Lab number 2 was about transformer, short circuit test, open circuit test. And then I think you did induction motor, right? And then you will be doing, I think, variable frequency drive operation. That is still induction motor. And then later you will be doing synchronous generator experiment, and then lab number 6 that I was telling today. Now you will remember, so when you are doing the induction motor experiment, probably you have noticed that you are also running a generator, right? Because I mean, for example, this is induction motor, and then its shaft is rotating. So meaning that because the shaft is rotating for the induction motor, you are applying the 3-phase voltage and that is rotating. Now you want to utilize this rotation. Therefore, you are starting a generator with the shaft, because you know that generator requires the shaft for its voltage production. That's why you are using a generator, meaning that that generator is working as a load of your motor. So that's why even though your focus is on the induction motor experiment lab number 3 and lab number 4, but still you are connecting with a generator to show that generator is a load of the motor, because it will not just spin, utilize the speed, utilize the rotation. That's why you are using the generator. The same thing in lab number 5 and lab number 6, the day you will be using the generator, because generator will produce voltage. Therefore, what you will do with the produced voltage? Then run a motor, for example, the induction motor. Therefore, for lab number 5 and 6, although your goal is to do the generator experiment, but with the generator, motor will be connected. And if you change the speed of the motor, then the terminal voltage will change. So that's why you are using the motor, meaning that induction motor will be the load for that experiment. That's why, I mean, don't be confused. I mean, what I am saying that lab number 3 and lab number 4, those are the induction motor, but still you might need to use the generator. Therefore, for lab number 3 and 4, generator is working as a load of the motor. Lab number 5, 6, you will be doing the generator experiment, synchronous generator, but still you will be running a motor. The motor will work as a load. That's why it is like together, in pair, always generator, motor together, motor generator together. Same thing in lab number 7 and 8. Lab number 7, 8 will be about the DC generator, and then 8 will be DC motor. The same thing. You will be doing the DC motor, but still you need a generator. Generator will work as the load of the motor. For experimented, it will be motor, but still you need generator. Therefore, always motor generator will be in pair. They will be together. Everybody, do you understand what I said? Could you follow me?
Yes, on my end, yes.
Yeah. Therefore, I mean, what I am saying that don't be confused that why, I mean, my experiment title is the motor, but I need to use the generator. That thing I am telling. Or my experiment title, lab title goes the generator, but why I need to use the motor? I mean, it's like vice versa. The motor will be the load for generator, and then generator will be load for the motor. That's why it is called motor generator pair. It is called like MG. It is called MG pair, motor generator pair. Yeah, it's always together to do the experiment. And why it is pair? Because these are not the the realistic real generator. Because in real generator, when it is in real power plant, you will have really coal plant or gas or steam turbine or nuclear. Really, there will be the prime mover. But here you see, because we are doing inside the laboratory, we are not using those things. That's why the day you are using the generator, you need your prime mover. So your prime mover is coming from a motor. That motor is working equivalent to nuclear turbine or gas turbine or steam turbine. That's why you need the motor. That is the meaning. That's why it is called the MG pair, motor generator pair. Okay, now actually I wanted to discuss that the synchronous motor, but like that thing came in my mind so that you don't be confused in the lab. Okay, now everybody look, the synchronous motor principle. I am going to discuss synchronous motor principle. Okay, so because this is motor, so this is my shaft, and of course it has that north pole and south pole, and this body is armature similar to the induction motor. Of course it has a three-phase system. Okay, so therefore this is, for example, A phase, B phase, C phase. This is the synchronous motor. So the difference between the synchronous motor and induction motor, this body, stator is the same. This body is stator. But the rotor, you see, the rotor, there is no coils. There is no winding on the rotor, but there is physical magnetic poles. There is physical magnetic poles. Now you remember, in case of induction motor, you don't have physical magnetic poles. You remember, with the help of reactive power supply, you produce the required magnetization. So that is the difference. Like I will be asking you difference. What is the basic difference between synchronous and induction? So armature is the same, but the difference is in terms of magnetic field. It has physical magnetic field for synchronous motor. Also, its rotor circuit does not have similar windings as to the armature or the stator. But in case of induction motor, you remember, there are similar three-phase coils and there were no physical magnetic poles. Now, okay, everybody come back. Because this is motor, what we have to do? I have to apply the voltage. This means I have to apply the current, in other words. So, okay, so my A phase current, B phase current, C phase current is going into the machine. So once I apply the three-phase voltage or three-phase currents to these coils, what will happen? Exactly the same thing that we have learned in case of induction motor. It will produce a rotating magnetic field. It will produce a rotating magnetic field, which is like phi s. And that phi s, what will be its speed? The same thing that we have learned in case of induction motor, synchronous speed, ns 120 f over p. Exactly this will be the speed of that magnetic field. Keep in mind, this speed is still not the shaft speed. Because we are discussing synchronous motor, ultimately we want to make it rotate, but still it has not started rotating. Keep in mind. So therefore this speed is this three-phase rotating magnetic field speed. Okay, so fine. We got three-phase magnetic field. Now what is the meaning of that? What is the meaning of that? For example, you have a coil and it caused the flux. So what is the meaning of that flux? Flux means it has the north pole and south pole, right? That is the meaning of the magnetic field. Therefore, here, once it is rotating magnetic field, this means it has north pole and south pole. For example, at the minimum, there are two poles, north pole, south pole. But everybody now look on the rotor. On the rotor already I placed the physical magnetic poles. These are physical, this north pole, south pole. But this north pole and south pole, this is internal. You cannot see this. This internal pole, north pole, south pole, created because of the application of the three-phase voltage or three-phase current on the stator coils. Now, what will happen? Everybody look. Initially, motor is not starting, meaning that because your north pole, physical north pole and south pole are placed on the rotor body, initially they are not moving because shaft is static. So, but this one is moving. You look, this North Pole and South Pole is moving. So meaning that because this North Pole and South Pole is moving, what will happen? This is static in position initially, this physical pole. So when this North Pole will be aligned, you see in that fashion, what is the reaction of the North and North Pole? It is attraction or repulsion. It will be repulsion. So what will happen when this rotating North Pole will be aligned, perfectly aligned with North Pole? Then like it will repel. This is moving in this direction, but this physical pole will little bit repelled on the other direction. Repulsion, not attraction. Then everybody see, once this south pole will be aligned here, like this is south pole and then this will become north because this is rotating. So what will happen? This south and this north, then it will be attracted. And but because this is the direction of rotation of the internal field, so therefore North Pole will be little bit attracted in that way. So it will be little bit just attracted, but cannot fully go. Why it cannot go? Because it has the inertia. You see? So from the physics, you know, it has that inertia. Because it has a specific weight, it has a specific mass. So it cannot immediately start moving. Just depending on the North Pole, South Pole, its alignment position, either it will be repelled or it will be attracted. That's why it will just be a little bit vibrating in direction, but it cannot be fully synchronized with this magnetic field. Because this is, you see, at that speed it is moving, 120 F by P. This is moving. And then depending on the North Pole or South Pole alignment, it is just able little bit go in that way or that way, attraction or repulsion. It is not able fully to move because this rotor has a certain mass and it has a certain inertia. So it cannot fully overcome the inertia. That's why it is called that synchronous motor is not self-starting. The construction I have shown, using this construction, it is not, the shaft is not able to move. This means that that shaft is not moving, a little bit just vibrating. Everybody, could you follow me so far?
Yeah.
Yeah, but then what is the goal of a motor? My goal is that I must rotate this shaft, right? I want the rotation. It is not the objective that, okay, you will just make the shaft and you will just explain to the people that synchronous motor is not self-static. That is not the end of the story. You have to make it rotate. So what to do? So that's why what you have to do, I mean, let me omit this one. So what you have to do, I can put a specific coil. Everybody look, this is the rotor body. On the rotor body, now I put a specific only one coil. What is the objective of that coil? Now you remember, everybody remember the induction motor principle. Why the induction motor was rotating? Because there are no physical poles heads, but there was 3 coils. And what happened? This rotating magnetic field caused the voltage on these coils. And then there was current flow, there was another flux, there was interaction of the 2 flux, and the motor started rotating. So exactly because of the inertia, initially synchronous motor is not running, I have to place a coil. This coil is called the damper coil. Everybody remember this? It is called damper coil or the damper winding. So meaning that damper coil or damper winding, it is placed on the rotor circuit to initially help the motor started. And once the motor is started, then you don't need this coil. So therefore now everybody see what happens. Now with this arrangement, I put a coil. So what will happen now? What is the sequence of operation? You applied the 3-phase voltage. It produces the rotating magnetic field. And then because there is coil, this magnetic field will produce voltage on this coil. and consequently there will be current flow. There will be another flux here on the rotor, sorry, there will be another flux on the rotor body. This flux, this is called the phi d. I am using the phi d to indicate this is the damper coil. And now there are two sets of flux. This is phi s and this is phi d. There will be interaction and there will be the torque. Now there are, you see that there are physical poles, north pole, south pole, because already this coil is helping to produce some value of the torque tau. So what will happen? The originally I was explaining, when this north pole and south pole will be aligned, then it will start be attracting, and already it has gained some torque. So then it will be fully locked and it will start moving. Ultimately, this shaft will start and it will be fully synchronized. And that shaft, it will gain the same speed, ns, which is 120 f over p. So in this case, what will happen? This shaft will also have the same speed. This means in this case, your magnetic fields, stator magnetic field speed, and finally the shaft speed is the same. So therefore, everybody look, I understand that that shaft has started rotating. It overcome the inertia with the help of the damper winding, and it is rotating at the same speed. So if it rotates at the same speed, then what will happen? Next time, will there be any voltage buildup on this damper winding? The answer is no, because the condition of voltage buildup, voltage development, there must be relative difference in speed. So therefore, this is the rotating magnetic field, which has, if 3000 RPM, then I am saying that shaft has also 3000. And that coil, the damper coil is placed on this body. It is attached to the shaft because it is connected to the rotor body. So therefore, this is moving means, shaft is moving means this coil is moving. And this magnetic field, and they are at the same speed. So next time, there will not be any voltage built up on the damper winding. But then there is no problem, because already this physical north pole, which are attached to this rotor body, they are started moving in. They have started rotating. So you are fully fine. Only problem at the beginning. So without the damper winding, synchronous motor cannot get started. It will just a little bit vibrate this direction or this direction. Everybody, now could you follow me?
Yeah, seems fine.
Yes. So therefore, that's why, I was discussing that thing. Now let's go back there to that slide. Then you will refine. Everybody read. Synchronous motor is not self-starting. So therefore, if you are asked why it is not self-starting, so how would you answer that one? You have to tell that because a rotor has some inertia, rotor has some mass. Therefore, initially, it cannot overcome that inertia. It will little bit just oscillating and vibrating. It is not self-starting. So how to start the motor? So you see, I have written it here. The role of damper or amortisseur. Oh, sometimes in the literature, you will notice this keyword. It is called amortisseur. Amortisseur, this is basically the same thing, damper. So this came according to the name of the engineer, like amortisseur winding. So what I have written, in case of synchronous motor, damper winding is used to initially start the motor, since the motor is not self-starting. So therefore, because synchronous motor is not self-starting, how to start it? With the help of the damper winding. And then how damper winding helped? It started with the principle of induction, and later it got synchronized. That's why synchronous motor is called induction start, synchronous run motor. So everybody, could you follow me? So these three things. So I mean the why. So you will be asked that question: why is synchronous motor called induction start synchronous run motor? So therefore, you would answer in that way that because synchronous motor is not self-starting, initially we have to start it with the help of induction principle by utilizing the damper winding. So therefore, with the help of damper winding, it follows the induction principle, and then it gets started, and later it's synchronized with the synchronous speed. That's why it is called induction start synchronous run. This means when it is running at full speed, that is at synchronous speed. When it is starting, it does not have the synchronous speed. It is following the induction principle. That's why induction start synchronous run. I mean, pretty interesting, the name of the synchronous motor. Now, like when we started the synchronous generator, we did not talk about the damper winding, because in case of synchronous generator, that shaft speed came from the prime mover. It is nuclear or gas turbine or steam turbine or water turbine, whatever the turbine. Synchronous generator has the shaft, but that was rotating from the beginning with the help of the prime mover or the fuel source. In case of the motor, you have to apply the electrical power to get it rotated. But at that time, I did not mention that synchronous generator has also the damper winding. Because today I am talking about damper winding for synchronous motor because it is the essential component for synchronous motor. That's why today I am telling you that information that I did not tell before. The damper winding is used to provide damping torque to eliminate hunting and restore synchronous speed of the rotor. Meaning that in case of synchronous generator also damper winding is used. Now the question is what I said, why it is used? To provide damping torque to eliminate hunting. So what is that hunting? So I have written down the definition of hunting of synchronous generator. Oscillation of rotor due to change in load is called hunting of synchronous generator. So do you understand what is the meaning of this? The meaning is that in real practice, always the load is changing. Like think about your home. Always like either you are turning on light or off, you are turning on your television or you are cooking, other time you are not cooking. Continuously your load is getting changed. You are changing your setting of your thermostat or the HVAC system, some sort of load. It's same thing in the university. One classroom is used and then other classroom was not used, but other time like all classrooms are used. The professors are staying in their office, other time not staying. In that way, continuously load is being changed. So that change, even though you can argue that, hey, I am changing only 40 watt load or 30 watt load, but think about a big community. At your home, you are changing 30 watt load, 40 watt, that is right, but think about a community. Then in that, like several megawatt load is always being changed. So then what is the impact? That impact go on the rotor. And that cause always some sort of oscillation in the rotor. That is called the hunting. So therefore, to understand this on, I mean, I think although I told you that always, let me show you one equation, then you all will easily get it. Let me erase all of these things. So everybody, you will keep in mind this equation. For example, this is your synchronous generator and this is that shaft and it is producing power. I mean, just take this simple example. Okay, it is producing electrical output power and that shaft is giving you the mechanical power. So therefore, everybody see I'm writing one equation here. Phi A equal to that phi M minus phi A. So phi A equal to Pm minus P. So, and then ideal condition, it is 0. So everybody look, what is the equation? Phi M is your mechanical power that is coming from the shaft. Phi A is your electrical output power. I mean, although I have shown online, assume that this is three-phase system. So this is your electrical output power. And then what I said, that equal to 0. This means I am assuming that the difference is 0, and that is the ideal condition. That is not in real practice, that is the ideal condition. Meaning that I am not considering any losses of the generator, like stator loss, copper loss, history loss, friction loss. I am assuming all losses are constant. My input power that is coming from the prime mover equal to the electrical power. Now everybody look, I am actually explaining you that hunting. My intention is to explain you that hunting of synchronous generator. What is the hunting? So everybody look, this is the electrical power. So customers are connected. Load means these are the customer. Customer are connected on the electrical side. They are electrically connected, but this side is mechanical. So meaning that I said that this should be 0. But what is happening? Always like you are changing some load. You see, for example, this is your 100 megawatt, that your PM, and this is also the 100 megawatt. This is the ideal condition. And then I am getting 0. But as I was explained you a few minutes back, always either I am increasing this phi value or I am decreasing this phi value. Think this total 100 megawatt that consists of all light, bulb, refrigerator, HVAC, whatever load you have in your house. And then continuously either you are increasing or like you are decreasing. It is happening. So therefore, always it is not 0 because of this change. This side is fixed. Everybody look, this PM value is fixed because that is coming from the mechanical system. I am assuming that there is no disturbance, there is no change in that, unless it is some emergency and some problem happen in the fuel input side. My assumption is that this side is fixed. This side is in the customer hands. So continuously you are changing something. So if you are changing something, what is the value here? If P value is larger than PM, then you will be getting negative value. And if P value is smaller than, then you will be getting the plus value here, right? This means always there is some number plus minus here. And then you see I have used one thing here, phi A. It is the accelerating power. This is called, this is accelerating power. Meaning that this is mechanical power, this is electrical power, and their difference I am calling accelerating power. So meaning that, you see, when you will be getting the positive result because the P is low, your system will be accelerated. On the other hand, when P value will be very high or higher, larger than the PM, then you will be getting negative value, meaning that it will be decelerating. Instead of accelerating, you will be calling the negative result decelerating. What does that mean? Your shaft speed will change. When you look, when P is low, you are getting positive value because accelerating power, your shaft speed will increase than the normal speed. When it is the negative, meaning that your shaft speed will decrease. And you remember, depending on the shaft speed increase or decrease, this is my equation, 120 F over P. What is happening? Because my pole number is fixed for synchronous machine. But if the speed change, increase or decrease because of this situation, my frequency is either increasing or decreasing. It is no more than 60 Hertz, either a little bit higher 60 Hertz or little bit lower than 60 Hertz. So meaning that if you change the load continuously, as a customers, we are continuously changing load, meaning that we are continuously changing the shaft speed. It is continuously like some sort of vibrating. And the frequency is also kind of the vibrating. It is also changing. It is never ever in real practice 60 Hertz, very close to 60 Hertz. because of this change in frequency and change in shaft speed, that is called the hunting. That is called the hunting. Everybody, could you follow me?
Yeah,
Yes. So this means the hunting is the oscillation of rotor speed due to change in electrical power. And that is coming from the nature. That is our behavior, our characteristics as a customers. We are continuously changing. Input side is fine, but electrical side where in real practice continuously changing. That's why in real practice, frequency is never ever like perfectly 60 hertz, either a little bit higher or a little bit lower. But of course, in United States, the frequency tolerance is plus minus 3%, plus minus 3%. If it is plus minus 3% of that 60 hertz, then it is fine. When it goes beyond plus minus 3%, then that is problematic. I mean, that is the different talk, we will not be going. But at this point, you just give what is the hunting. And then to eliminate that hunting, that I was telling, that damper winding is used. You see, in case of synchronous generator, damper winding is used to provide damping torque to eliminate hunting and restore synchronous speed of the rotor. Because you see, the hunting is the oscillation of rotor speed due to change in load. So with the help of damper winding, we can eliminate it. That's why damper winding is used in both synchronous generator and in the synchronous motor. So therefore, this will be the question. I will be asking you the question, what is the role of damper winding in synchronous motor and synchronous generator? You will be answering that. In case of synchronous motor, damper winding is used to initially start the motor because motor is not self-starting. On the other hand, in case of synchronous generator, damper winding is used to eliminate the hunting effect so that the speed can get restored. Speed can get back to the original rated speed. Okay, I think it has been like 11:09. So I like to stop here today and then I will be continuing the synchronous motor. So is everybody fine so far?
Yes.
Yeah.
yeah, I think so. Everything looks good.
Yeah. So please you look, and then again I will be explaining much more in the next class. So everything will be fine. Okay. So at this point, let me stop sharing.